This is Phoebus 2A operating at full power. It was the largest and most powerful reactor yet tested in the rover program. Phoebus 2A was designed to operate at a power level of 5,000 megawatts, nearly 4 times that of Phoebus 1B. The core was constructed in a manner similar to the previous reactors of the Phoebus 1 and Kiwi B4 type. In this design, 6 hexagonal fuel elements were arranged around a central unload support element to form clusters. These clusters, when stacked together, formed the core of the reactor. Because of its larger size, 2A required the use of a total of 4,000 fuel elements, 2,500 more than 1B. In all, a total of 77,132 metering sleeves were installed in the propellant passages of the elements. In order to ensure accuracy during assembly, the calculated metering sleeve sizes were printed out graphically to provide the operator with a visual plan of the sleeves for each cluster. As a further check, color photographs were made of the cold end of each cluster. Color coding of the metering sleeves provided positive verification of the accuracy of the assembly. A second photograph, made looking the length of the cluster through the sleeves, was used to inspect for obstructions in the metering sleeves and propellant passages. To measure fuel element corrosion, the Los Alamos Scientific Laboratory has developed the new inspection technique known as MULE, an acronym for Mass Per Unit Length Examination. During this inspection, the fuel element is passed through a gamma beam from a cobalt-60 source. Measurements of the intensity of the beam transmitted by the element are taken every inch over its entire length and recorded for later comparison with similar measurements made during the post-mortem analysis. Unlike its predecessors, 2A was assembled in an inverted or cold end-up position. This method of assembly was chosen to eliminate the possibility of any shifting or twisting of the clusters during assembly. Tie tubes were used instead of tie rods to support the clusters of fuel elements. The tie tubes were cooled by a separate flow of liquid hydrogen, which rejoined the main hydrogen flow at the core inlet plenum. This regenerative flow system marked a major performance improvement because it avoided discharging low-temperature hydrogen into the nozzle chamber. This allowed higher exit gas temperatures, which resulted in an increase in the specific impulse of the rocket engine. To ensure firm seating of the elements against the support blocks, each element was fitted with a spring. The 6 springs in each cluster were held in compression by a common cluster plate assembly at one end and a screen cap assembly at the other. The screen inside the cap assembly served as a filter for the propellant. In order to better withstand the greater radial pressure drop of a larger diameter reactor, the graphite reflector cylinder used in the Kiwi and Phoebus 1 reactors was replaced with an aluminum interface cylinder. Because of the difficulty of fabricating a graphite part of this size, this decision offered added advantages. Phoebus 2A's larger core size required an increase in the number of control rods from 12 to 18. Improved cooling of the control rods was achieved by using a system of stationary rods enclosed in rotatable drums. A layer of boron carbide copper cermet, 1/10 of an inch thick, was attached to 120 degrees of the surface of these aluminum drums to act as the neutron absorber. Since the rods were stationary, coolant passages could be placed in them in optimum positions to allow for the greater heating nearer the core. Another advantage gained by this design was to avoid the use of larger rotating control rods, which would have an undesirably high mass and moment of inertia. Phoebus 2A was delivered to the test cell on April 9, 1968. nozzle, supplied by Aerojet General Corporation, was fabricated from the 3 largest forgings of Hastelloy ever produced. Hastelloy X is an alloy of nickel, chromium, and molybdenum. It was chosen because it can survive in a temperature range from minus 423 degrees Fahrenheit to 2,000 degrees Fahrenheit, the environment which the nozzle could expect to experience during the full power run. The liquid hydrogen, which entered at its exhaust end, cooled the nozzle as it flowed axially through its lining of tubular passages to the reactor. A new shield, half again as thick as that used for 1B, was provided for the more powerful 2A. Borated water, to act as a heat shield and neutron absorber, was pumped through the shield and privy roof at a rate of 5,400 gallons per hour to provide a complete change every 40 seconds. 1 million gallons of liquid hydrogen, the amount estimated necessary for the 20-minute run, was stored in 2 dewars which supplied the reactor and the turbine energy source. Some liquid hydrogen was diverted to a heat exchanger which produced the gaseous hydrogen to power the pump turbines. In order to provide the greater volume of liquid hydrogen necessary for the more powerful 2A design, 2 turbopumps were used for the first time. These were the Rocketdyne Mark 25 turbopumps, which delivered liquid hydrogen to the reactor at a rate of 540 gallons per second during the full power run. The liquid hydrogen supplied to the tie tubes during the run was controlled and monitored from the control point. On May 22, 1968, reactor operators began the first of 3 experimental plans to evaluate the reactor, its interreactions with measuring instruments, the test cell facility, and the many systems needed to test the reactor or support the test operation. A second experimental plan was conducted on May 29th, and a third on June 8th, at which time the reactor was brought to intermediate power for a brief period. On June 26th, Phoebus 2A was given its high-power duration test. It was the largest nuclear rocket engine ever tested. A number of steady-state holds were performed on the programmed run profile to obtain neutronic reactivity data. When the hold at 4,100 degrees Rankine, 4,100 megawatts, and 260 pounds per second hydrogen flow rate was reached, the temperature of the pressure vessel main closure was at its red line limit, and a decision was made to go no higher in power. The reactor was operated for 12 minutes at these conditions, at which time a programmed shutdown was initiated because the planned amount of turbine energy source hot water had been expended. 3 weeks later, on July 18th, the reactor was tested again at a power level below 4,000 megawatts. The objectives were to perform controls experiments not completed in other experimental plans, to expand the reactivity mapping done on EP4, and to perform an emergency shutdown from an elevated power level. At the 160 pound per second hold, an unplanned emergency shutdown occurred, and the emergency shutdown system operated normally. After a routine cooling period, during which liquid nitrogen was used briefly as a coolant, the reactor was restarted. The second run was successful. Finally, at a temperature of 2,700 degrees Rankine and a flow rate of 195 pounds per second, the planned emergency shutdown was executed. The initial phase of the shutdown went smoothly, but after a few seconds, the flow to the reactor dropped to a very low value, and overheating of the tie tubes occurred. After gas flow was established, the cool down progressed normally. The reason for the loss of flow was later determined to be plugging of the propellant pipe filters. Frozen nitrogen slush had collected in a dead leg of the pipe during the cool down following the first emergency shutdown. On July 24th, The reactor was disconnected from the test cell and moved to the RMAD building for disassembly, which began the next day. When the nozzle and pressure vessel were removed, a view of the end of the core revealed a large percentage of the tie tube assemblies had parted at the support braze joint. This was caused by overheating that had occurred during the loss of coolant following the planned emergency shutdown. This damage did not affect the rest of the core, and the disassembly and post-mortem operations were completed smoothly. All of the major mechanical components, such as the nozzle shown here, were in good condition. The fuel element weight loss and mid-band corrosion were somewhat greater on the average than had been anticipated. Good results, however, were obtained with the experimental elements, which used a new coating technology. These elements were made following production of the bulk of the core. The Phoebus 2A test series successfully demonstrated the design and operation of a large high-power density reactor having a regeneratively cooled fuel element support system. The power and flow rate were approximately 3 times as great as the maximum values previously attained in the nuclear rocket program.